afternoon, and welcome to those who may be watching this webinar recorded. My name is Stephanie Lewis. I will be your moderator for today's National Institute for Congestion Reduction webinar. It is my pleasure to introduce you to multi-stage models for dynamic ride sharing in taxi services and congestion analysis, a case study in Chicago. Normally, I would do our formal introductions of our presenters today, but they would like to do that themselves. So with that, I'm going to now hand the presentation over to Chang. So Chang, go ahead and take it away.
Yeah, hello everyone. So we're gonna to present our research results to everybody here on the multi-stage models for dynamic ride sharing mode to everyone in the taxi services. Also, we do the congestion analysis. We use the data set, the taxi data set in Chicago. So let me introduce our team to everyone. We got Minchi. He's a PhD student in Texas A&M, and his major is transportation engineering. We also got Yunil from UC Berkeley. He's also a PhD student in Texas in UC Berkeley. His major is also transportation engineering. So this is me. I'm Chang. I'm also from Texas A&M. My major is transportation engineering too. So I will go through a little bit about the outline of our presentation today through introduction until the conclusion. So let me briefly introduce why we need ride sharing. So in modern society, so we got a lot of vehicles running on the road that may cause congestion emissions. So if we apply ride sharing mode, we can reduce the number of vehicles on the roadway network because we will reduce the number of vehicles, right? We will increase the occupancy rate among the vehicles on average. And then ride sharing also have the potential to promote because you can save the travel fee, fuel costs. Also, we can also reduce the congestion because we reduce the number of vehicles on the road. And then we also know that among the modern society, Uber, Lyft, those commercial companies, they use the ride-sharing mode in their application, but they may more focus on one request for one rider or two riders at most. So we will do this research to activate people's interest to show that how we can increase the benefits of ride-sharing mode. So we have the main goal here, which is to maximize the total mileage saving of the whole system. And then we also consider the passenger and driver's waiting time and the detour tolerance, because we have to make sure that riders and drivers, they have a really good experience when they go travel by ride-sharing mode. So as we said, we will allow more riders in per vehicle. So in this study, we'll propose like multi-stage model to include more user-centric factors. So we also did a literature review about ride-sharing mode. We find that in the past studies, they already got some study using some integer programming, also some algorithm methods to solve the ride-sharing model problems. They got some studies focusing on 2+ riders. Also, they also did some simulation process, but our research may focus on more riders and specific methods. So yeah, let me present it to Yunil.
Yep, thank you, Chang. So literature reviews for congestion analysis can be separated into 3 categories. First is congestion estimation through different methods, formulation of congestion index based on a different congestion matrix, and combination of different congestion matrix to form integrated congestion index. This slide presents the literatures that utilize different types of methods for estimating congestion status. The first paper utilized the pro-vehicle data and estimated the congestion status through dynamic Bayesian network, traffic theory, and probabilistic model. The second paper used the trajectory of vehicle and transform into cell network to construct a spatial and temporal traffic diagram. And then the third utilized the coupled hidden Markov model to estimate the spatial and temporal distribution of vehicle. This slide shows the literatures related to congestion index and congestion matrix. The congestion index is an index representing or identifying the congestion status, and it makes to understand and assess the congestion status directly and easily for both experts and general publics. And first paper utilized travel time index for the congestion index. Second paper utilized the ratio between average travel time and travel time under congested condition as a congestion matrix. And the final paper utilized speed and density for the congestion index. And this slide presents past works that studied the integrated congestion index using different methods and different congestion matrix. First paper integrated flow, volume, and occupancy using fuzzy C-mean clustering. The second paper combined travel time-based congestion index and volume to capacity. And then the final paper used the fuzzy logic to combine speed and density for the integrated congestion index. I would like to hand over to
Thank you, Yunil.
Yeah.
And we'll continue our presentation on the ridesharing method and some social results of the study. So we did make some assumptions before conducting this research. So as we said before, we will continue on conducting this research on maximum 4 passengers in a match for each vehicle. And we assume that each vehicle will run in a constant speed. We consider both their waiting time and the tour allowance into consideration. And then we also need to consider drivers will have a parking limitation where they have to wait for a passenger. So we start with the time frame using the insertion method, and the second part is the optimization. So we will consider each possible combination of the riders. So we have to pick out each passengers from a location and then to drop off them. But there are a lot of combinations, so we have to use the insertion methods to consider the potential matches identification for each possibility. After the first step, we'll go into the second step, which is to select the best combination that will make our mileage saving, which is the maximum value. And then after the 2 sections of the time frame method, we'll move to the next time frame. So we'll go to the next step. Minchi?
Okay, thank you, Chen. Can you hear me?
Yes.
Okay. Now let's talk about the insertion methods. So the insertion methods means that we try to insert a rider's trip into another. So for example, in here you can see that we try to insert another people to the original trip, and then we got the third one. So this is the concept, and we separate our process into 4 stages. So at the first stages, we will pair the 2 single rider together to get the 2 rider matrix, and then we try to combine these 2 rider matrices, and then we can get the 4 rider matrix. And still, we may still have some unpaired single riders. So we use that rider and to pair with the matrix from the stage 1, then we can get 3 rider matrix. And then we keep doing that. We still have some unpaired rider, and we try to find that unpaired rider and to pair them with the 3 rider matrix, so we can get 4 rider matrix. So this is the whole process of our insertion methods. And now the problem is this insertion methods is just to make sure that we can get a beneficial matrix, but how to choose? Now, before we talk about that, let's assume that we can get this information from the rider. We'll know the destination, we'll know the rider's expected pickup time, and we'll know the maximum waiting time of the rider and their detour tolerance. So with this rider's information, we can formulate the problem. This in the beginning, we will examine if this metric is beneficial, and this is related to their destination, which is distance. And then we will consider if they wait too much time. So this is related to the question of their pickup time and their waiting time, or maximum parking time. And then we will examine whether this rider traveled too far. Then this is related to their detour tolerance. And remember that we got this information from them, right? Now let's talk about this formula one by one. So first, we talk about beneficial matches. And beneficial match means that the summation of the distance should be smaller than the distance without ride sharing. So here in this case, if this dashed line is the ride sharing distance, then the summation of this distance should be smaller than the summation of this blue and green line. Otherwise, there's no point to have this ride sharing. And second, we will examine the time, whether the rider wait too much time. Now let me use this element to give you the concept. So assuming that the expected pickup time for the rider 1 is 8:55, and we know that it took 10 minutes driving from rider 1 to rider 2, and the expected pickup time of the rider 2 is 9 a.m. So if the taxi pick up rider 1 and go to pick up rider 2, it will arrive at the location of rider 2 at 9:05, which means the rider 2 have to wait for which means the rider 2 have to wait for rider 1 for 5 minutes, because the riders already wait here at 9 o'clock, but the taxi come 5 minutes later. So we will examine here if this is small. This is -5 minutes. So we'll examine whether this is smaller than the maximum waiting time. Now, in this case, the maximum waiting time of the rider 2 is 50 minutes. Then we know that this constraint is satisfied. If the maximum waiting time of the rider 2 is only 1 minute, then we know that these two riders cannot be paired together. Now let's talk about the case 2. If the expected pickup time of the rider 1 is 8:40, and then when the taxi arrives at rider 2, it will be at 8:50, which means the driver have to wait for rider 2 because it arrived here 10 minutes earlier. Then we will go through this formulation here. Then we will, because this is positive, so we'll go through here this formulation, and we will check if the time will exceed the maximum parking time. So in this case, the maximum parking time is 5 minutes, and here the taxi waits for 10 minutes, which means that these two riders cannot be matched together. So this is the concept of the time consideration. However, this concept only works for two-rider matrix. But as mentioned, one of the features of our research is to apply this method to multiple riders. For example, in this case, we have 3 riders. But if we use the previous method, this rider 3 may assuming that, okay, the pickup time of the rider 2 is 8:10, and it took 20 minutes drive, then it will arrive at around 8:30, right? But in reality, the taxi comes from rider 1. It comes from here, so it will keep the delay time will be added together. So we have to consider the delay time. So if we consider the delay time, actually the rider waits for 25 minutes instead of 15 minutes, which means that our previous formulation is not good enough to do that. So we improve it by introducing the T current time during our process. So this is a dynamic updating process to update the current time. Basically, we use the T current time to replace the pickup time of each rider. So the rider 3 will not look at the pickup time of rider 2 anymore. Instead, they will look at the current time. So by using this method, we can find a more reasonable pairing And the last one, the last consideration is the detour tolerance. Detour tolerance means that the distance of the rider in ride sharing will not exceed too much of their ideal distance. So, for example, in this case, without ride sharing, we know that the rider one will go this distance, right? In the ride sharing, the rider one will have some detour. So the concept of this constraint is that the dashed line cannot be too lengthy. If it's too lengthy, like go this way and go this way, then the rider one will not want to join this game because it has too much detour. So we use this to exclude some unreasonable pairing. And the insertion methods mentioned above is only for the to identify the potential matches, but eventually we still have to determine which riders should be paired together. And we will use the greedy algorithm and the binary programming to compare and to see which one has the best performance. So regarding the greedy algorithm, it means that we want to choose the pairs by the order of saving without having a rider in two pairs. So assuming that this is the network of the rider, each node means a rider, and this link means that these are beneficial pairing. 20 means that if these two riders can be matched together, then these two riders can save 20 units of miles or dollars, depending on what kind of the cost. So if we use greedy algorithm, then we'll find that we will choose this first because this is because they can save 25, right? So if we choose this link first, then these two users are excluded from this game. Then we choose this because the two riders are not paired so far. So in total, we can have 35 total saving. So this is the concept of the greedy algorithm. It's pretty straightforward. Then let's introduce another method. It's called binary programming. So, but this is a kind of the objective model. We want to maximize the total saving in the system. So this Xij means that if the rider I and j can be matched together, so it can be either 0 or 1. It means whether I choose this thing or not. And we still we have this constraint. It means that each of the rider cannot be paired to two links. It can only be paired to one link. So let me use this previous case. If we use binary programming, because our objectives is to maximize the total saving, so the system will give us an answer of this link and this link, because the summation of these two links will be 40, which is larger than the previous one. So this is the concept of the binary programming, and we use both of them. Now let me summarize our matching process. So before ride sharing, we have a lot of unpaired riders, and in this stage, we will try to look for the potential matches of two rider match. So assuming that this dash green line are all potential matches, so we try to match them together. You can see this man will go here, get these two. This will go here, get these two, and we have two potential matches here, right? And because of the constraints that only one matches, only each users can only be matched to one link. So this go here, and this man will be still saving the same price because we can only choose one link. Same as the previous method, we try to look for potential matches of four rider match. Then here we find these two dash orange line, and we can only find one because this is overlap. So then we find we turn out this, assuming that this is more beneficial. So they are matched together and we still live here. And then we use insertion method to insert the third rider matches. So here this is put this rider is inserted to this matches, which is there. And yeah, we keep doing this to pair this unpaired single rider to the existing three rider matches. And in the end, we get four rider matches and those unpaired riders. And this is just the insertion process happening in one time frame. If we want to examine the whole day, then we will go through this process in each time frame. It can be either 50 minutes, 30 or 30 minutes, depending on our data. So with this method, we will have the output of successful 4-rider matches. And we still have a lot of unpaired single riders and 2-rider and 3-rider matches. So these rider matches will be put into the time frame 2, same as the unpaired single rider. So they will be put here, and then because we have a new rider in time frame 2, so we will doing this insertion process again. Then we will have successful 4-rider matches, and we will exclude the old rider matches from time frame 1 to reduce the burden of the system. Then we keep doing this, and we will have the successful 4-rider matches, and we'll keep expanding the 2-rider and 3-rider matches in the system. And we apply our proposed ride-sharing method in the Chicago city. So from this figure, we can find that most of the trips happen in the central district and airport area. And because we got this testing data from Chicago government, and because the government has to protect the privacy of the rider, so the pickup location and the drop-off location of each rider is represented by the center of each central district. I mean, of each district. So in other words, if we have 2 riders from this to this place or from this region to this region, we only know that their location is the central of these nodes. So we don't know their the precise drop-off location or pickup location. So this is like the limitation of our data. And we examine the distribution of our trip number, and we find that after 8 a.m., the number of the trips increased a lot until 6 p.m. And so with this data, we examine our proposed method. These two, the blue line is our proposed method, and we compare our method with other methodology. This two means that we can only have maximum 2 rider in the match, and this means that we try to insert extra rider to the existing 2 rider to get this for maximum 4 rider. However, this method doesn't have the matching of 2 combination. I mean, because our method combined 2 existing 2 rider matches together to get the 4 rider matches, but this method doesn't have that matches. So this is the result. The black line is the total distance without ride sharing, and the orange and the red line is our method. So from this, we can find that no matter we choose greedy algorithm or integer programming, we can still get a pretty similar performance. And same for this method 1 and 2. They are almost overlap. And by comparing our performance with this method, we can find that we have a big improvement. We totally reduce the distance by around 55%. And although this method has the maximum 4 rider in the match, but as mentioned, they lack of the matching of combining 2 riders together, so they cannot have a big improvement from method 1 and method 2. And this is the number of pairs for each rider. And here we can find that our proposed method can have a pretty good performance to form the 4 rider matches. And because for the method 1, method 2, they can only form 2 rider matches. They don't, because this is their maximum rider, so they have a 0 matches here for the 3 rider match and 4 rider match. And yeah, so we compare our method with the Manhattan distance and Euclidean distance. So these 2 distance means that based on our network, we will measure our distance based on the straight, based on the green network or just a straight line. And we can find that no matter which method we choose, if the detour ratio go upper 20% or 25%, then we can reduce the total distance by around 50%. So this is quite inspiring. If each rider is willing to travel 20% more of the distance, then we can reduce a lot of the total mileage. Regarding the computational time, unfortunately, if we use integer programming, the computational time will increase much exponentially because we have new riders keep joining to these systems. So this will have the burden to the solving of the integer programming. But for the greedy algorithm, which is the blue line, there's almost no influence. So our summary is that both of our proposed method can reduce the total distance by 55 and 56% with greedy algorithm and integer programming. But if we consider the computational time, then maybe the greedy algorithm will be better. And our proposed method can officially increase the four-rider pairing. And if the detour ratio reaches to around 1.25, then there will be a significant saving in the total distance. And however, these benefits are all limited to the side of the taxi, the side of the rider. So we still have to consider the benefit for the city, which is the congestion. So next, Union will help us to analyze the congestion.
Yep, thank you, Minchi. So this is the outline of the congestion analysis part. And the goal is to assess the traffic congestion status of the city of Chicago for each 15-minute interval with taxi trip data and rideshare trip data. Throughout a few next slides, I'm going to present about congestion matrix selected for this project, how each congestion matrix is computed, and how congestion matrix are combined to create integrated congestion index. In order to choose the congestion matrix for the project, it is important to consider the characteristic of trip datasets. Taxi trip datasets have information about each taxi trip, including when and where it picked up and dropped off the passenger, the travel distance, and trip duration. In order to protect the privacy of citizens, the trip datasets is masked so that the pickup time and the drop-off time is rounded to nearest 15-minute interval. In addition, the pickup and drop-off location is reported as a centroid of the community areas or census tract. Based on the taxi trip data characteristic, mean velocity is chosen as the first congestion matrix. Mean velocity is one of the common congestion matrices used to assess the congestion status. The left figure is showing the speed of the mean speed of the roads in the city of Chicago. And the right figure is a fundamental diagram showing the relationship between speed and flow. As both figures show, it is possible to directly and easily assess the congestion status through mean velocity. Higher the mean velocity, less congested the area or road is. The second congestion matrix is congested vehicle mile traveled ratio, or congested VMT ratio. It is a congestion matrix used by Metropolitan Transportation Commission in California. Left figure shows how congested VMT ratio is used to evaluate the historical trend for highway congestion in Bay Area. The congested VMT ratio is computed by dividing a VMT at congested status by total VMT. And similar to mean velocity, the congestion status can be directly and easily assessed. Higher the congested VMT ratio, the more congested the area and the length is. Now I'm going to talk about how the mean velocity of an area is computed. And the goal is to compute the mean velocity of community areas or census tract in the city of Chicago for each 15-minute interval with taxi trip data and rideshare trip data. It consists of steps of extracting possible areas crossed by a trip, computation of weighted mean velocity, and its adjustments. Since the data only consists of origin and destination of the trip, we do not know what areas were crossed by a vehicle for a trip. Therefore, we need to extract areas that a trip might have crossed. The figure shows the process of extracting the possible areas crossed by a vehicle for a trip. Purple area are the community areas in the city of Chicago. And A and B is a central location of origin area and destination area, respectively. With these coordinates, the rectangle is formed, which is shown in green. And any area that intersects with the rectangle is considered as the areas that a vehicle might have crossed before a trip, which is shown in yellow. By repeating this process for each trip in 15-minute interval, it is possible to have a list of trips that might have crossed for each area. Using mean velocity of these trips, the mean velocity of an area can be computed. However, the mean velocity of the trip should not be directly used to compute the mean velocity of an area. If a trip mean velocity is assigned directly, it means that the velocity throughout the entire trip is constant, which in real life would vary throughout the entire trips. In order to overcome this problem, the weighted mean velocity of these trips for an area is computed, and the weight is based on two values: travel distance and trip duration. Let's consider two trips that cross the green area as shown in the slide. If a vehicle travels for a longer distance, like blue trip, it is more likely that a vehicle to spend more areas, as shown in the figure. Then the mean velocity of the trip traveled longer distance, in this case blue trip, is based on velocity of more number of areas, as you can see. Therefore, when we assess the mean velocity of a particular area, the velocity of a trip with shorter distance would contain more information about the mean velocity of that particular area. In conclusion, the shorter the trip distance, the more representative the mean velocity of a trip to the velocity of an area. For this project, we have clustered the trips based on trip distance. Based on the statistical analysis, we create 25 2-mile intervals where trips with distance between 0.5 miles and 50.5 miles are distributed. In the figure, trips with the same color represents that the trips are in a same cluster. Instead of using the trip distance directly for the weight is going to be based on what cluster a trip belongs to. Weight of the mean velocity of a trip should also be based on trip duration. Assume that there are two trips, as figure shows. The trip with longer duration within 15-minute interval means that the vehicle stayed longer in that area. Therefore, the mean velocity of a trip contains more information about the mean velocity of an area in a particular 15-minute interval. In other words, velocity of an area is better represented by a trip with longer duration within 15-minute interval. Based on a trip duration and cluster, the weighted mean velocity of an area is computed. The weighted mean velocity of an area is going to be adjusted to have better estimates. The first adjustment is based on neighboring areas. So the neighboring area of a green area is blue in the figure. And it is based on the assumption that the velocity of an area and its neighboring areas are correlated. The second adjustment is based on the past velocity of an area. And it is also based on the assumption that an area's velocity at a particular 15-minute interval is correlated with the area's velocity at its previous time interval. Using the mean velocity of an area at particular 15-minute interval, the mean velocity of an area at its previous time interval, and the mean velocity of its neighboring area at the same time interval, the least square model for the final mean velocity of a community area is formed. For the next few slides, I'm going to describe how we computed the second congestion matrix, the congested VMT ratio. Due to the characteristic of a trip data, unlike mean velocity, VMT is calculated for entire city of Chicago instead of each community area or census tract, and each time period instead of 15-minute interval. The table shows the time period for VMT computation and its description. The time period is defined through this analysis on the traffic pattern in the city of Chicago. The below equation shows how to compute the VMT, which is based on number of vehicle, the average trips per vehicle, and average distance per trip. From Chicago Traffic Tracker, where the Chicago Department of Transportation provide the real-time traffic information online, speed greater than 20 miles per hour is considered no congestion or light congestion. Therefore, the congested VMT is computed by is defined as VMT of trips with speed less than 20 miles per hour. With congested VMT and total VMT, the congested VMT ratio can be computed based on the below equation. Now that we computed congested VMT ratio and mean velocity, the integrated congestion index can be formulated. And for next few slides, the process of computing integrated congestion index will be described. This is the table showing the congestion index defined for the project. And this is based on Chicago Traffic Tracker. Determining the congestion index, or CI, with a strict cut line can be problematic, since a small differences in a congestion matrix value can lead to a significant differences in a congestion status. Therefore, in order to overcome this problem, we use fuzzy logic and membership functions to find a membership degree in each congestion index for each congestion matrix. Fuzzy logic is a type of logic based on a degree of truth instead of true or false, like in a traditional binary logic. And fuzzy logic can capture the range and nuance in a congestion status. The figure shows the membership function based on a velocity. It defines how velocity is mapped to a membership degree to each congestion index. And membership degree represents the degree of value belonging to each congestion index. Based on the velocity, it computes the membership degree to each congestion index. And for example, if the velocity was 20 miles per hour, the membership degree to congestion index being 0 is 0. And membership degree to congestion index being 1 is 0.5. And membership degree to congestion index being 2 is 0.5. And the membership degree to congestion index being 3 is 0. And a similar process is done for the congested VMT ratio also. Now that membership degree to each congestion index for each congestion matrix is computed, the combined membership degree is computed as a weighted sum of membership degree. The greater weight on the membership degree based on mean velocity is given due to its higher spatial and temporal position. Mean velocity is computed for each area and for each 15-minute period, whereas the VMT was for entire city and for a time period that is longer than 15 minutes. For our project, we have utilized 0.7 and 0.3 for the weight. Integrated congestion index then is chosen by finding a congestion index with largest combined membership degree. Integrated congestion index then visually represented through a congestion map. Through the congestion map, it is easy to understand and assess the congestion status of the city of Chicago visually. The slide shows a congestion map of the city of Chicago based on integrated congestion index before ride sharing and after ride sharing in the morning rush hour and afternoon rush hour on January 9th, 2019. The congestion index of 0, 1, 2, and 3 is represented as brown, red, orange, and blue in the congestion map. The upper left quadrant shows the congestion map of Chicago in morning rush hour period before the implementation of ride-sharing system. As it's shown in the congestion map visually, there are areas with medium congestion status located around the downtown of the city of Chicago. After the implementation of ride sharing, as shown in upper right quadrant, the congestion status of an area previously in medium congestion got improved to light congestion. Similar observation can be seen in the afternoon rush hour. By comparing the congestion map in the lower left quadrant and lower right quadrant, some areas with medium congestion status got improved to light congestion after the implementation of ride sharing. These are the congestion maps for January 15th, 2019. And as we've seen in the case for January 9th, it is possible to notice the improvement in congestion status in some areas visually after the implementation of ride sharing in the city of Chicago for morning rush hour and in afternoon rush hour. In conclusion, the proposed ride-sharing model can significantly improve riders pairing and reduce the total distance by 55%. And the overall congestion status of the city improved by comparing the congestion map before and after ride-sharing visually. Due to the separation of multiple stages in a time frame, we may not reach the system optimal, but only the stage optimal in the specific time frame. And this study provides rider-to-rider matching models, and further work is needed to assign rider matches to drivers in the network. And that would conclude our presentation, and we would like to have a Q&A session. And I'll hand it over to Stephanie.
Thank you so much for all of the information. What I'm going to do now is, as we mentioned, is we will be taking some questions. Again, you can utilize that Q&A box in the lower right-hand corner of your screen. Simply type in any questions and or comments you have, and we will read those out loud. The first question comes in. It says, can you apply this model to scenarios with larger occupancy, for example, 10 or 10 or more riders?
Let me handle this one. That's a really good question. And so we just proposed here to handle, as we said before, like more than 2 riders per vehicle. So then if you apply, the vehicle capacity is 10 or more than 10 maybe, and apply this method to this scenario. We just propose a draft idea how to handle the cases with more riders per vehicle. Hope that answered that question.
Great. Yes, it did. Thank you. Are there plans to expand this analysis to other large cities? And would you expect to see similar results? And then I'll sort of follow up that question with what about in some in some smaller cities? For example, I'm thinking like Indianapolis, Nashville, as opposed to like a Chicago, New York City kind of um, um, size.
Yeah, I can answer this question. So, yeah, I think the improvement. So in this study, we said that the improvement is around 55%. But yeah, this improvement can be influenced by which area we apply and also by the network. So that's the purpose why we test our sensitivity analysis by Manhattan distance and also by the Euclidean distance. But also, and I mean the network of the traffic will influence, and also the OD metrics will also influence the result. So, for example, if we are in the small town and we only have a few metrics, and maybe it's pretty hard to match them together because we also have to consider the bigger time. If the time is to disperse in this in the whole day, then there's no way that we can match them together. So we think that this method will be more beneficial. We will have a more advantage if this applied to a larger city. If it's only a small town, then yeah, I guess the improvement may be limited to some degree. I hope this answers your question. Thank you.
Yes, thank you. Another question comes in. It says, when we look at the congestion map, there are a few areas where the congestion status got worse after implementation of the ride sharing. Why is that?
I can answer those questions. Just pull out the slides. So it is true. Some area, like for example, I'm not sure if the mouse is gonna work. So if you see this particular area, sorry, yeah, this particular area, you can see that after the implementation of ride sharing, the congestion status got a little worse. The reason is because when we do the ride sharing algorithm, we pair up the passenger and it goes to some areas that were not previously that would not crossed if the ride sharing is not implemented. However, if we just look at in general how the congestion map has changed, how the congestion status has changed overall in the city of Chicago, we can see that there is definitely an improvement in terms of the congestion status and overall. So it's kind of dispersing this distributing this congestion through different areas to make it every congestion status a little bit better in overall. So it is true there are some areas that congestion status got worse, but overall it got improved.
Great, thank you. It doesn't look like we have any additional questions, so I would like to thank our Minching, Unil, and Chang for the great. Oh, here, sorry, one more time, one more question. Uh, oh, uh, one of the professors would like to thank their students for the great job they did on this research. Uh, and you're welcome for the organization of the webinar. So again, thank you so much for attending today's presentation. I will take this moment to open up the evaluation for you on your end. If you could take a few moments to complete this evaluation, as the feedback provided is not only important to our presenters today, but the entire NICR webcast series. So on behalf of the National Institute for Congestion Reduction, thank you so much for attending today's webinar, and we'll see you all real soon. Bye, everybody.